So hello all. Today will be the last lecture in this particular course, and the material would be on clustering. So I would be covering the two major topics that were covered in the last week's lecture, that was k-means clustering, and the second was hierarchical clustering. So first I'll start with k-means clustering, then I would give you a brief overview of hierarchical clustering, and after that it would be like then I will have one or very simple questions, and then we'll stop. So yeah, okay, so let's start with k-means clustering. Right, okay, so as we all know that it's an unsupervised algorithm and it divides the data into k clusters. The point is k needs to be known from before. That is the assumption that you make for the k-means clustering algorithm, that the number of clusters you want your data to be partitioned into needs to be known from before. And it's a hard clustering algorithm in the sense that it does not assign probabilities to the points. It says that either this point belongs to this cluster or it belongs to some another cluster. So that is the k-means clustering. So I'll go by an example as that would be easier to understand also. And yeah, so that would be the crux of what k-means clustering. It's a very simple algorithm, but it works quite well in the sense that it is still till date k-means clustering is still being used extensively. Right, so what we have is we have three clusters. So these are the points, these are 4 and 7 points, and whenever a human being sees all these, they will find out, okay, these are the two, so there are three clusters of points, and so these are the three clusters. However, since the algorithm is unsupervised, you don't provide any of the colors to the machine, to the system, and therefore the algorithm will start with all points gray, which means that no clusters are assigned to any of the points, so all of them are gray. Okay, so that is how k-means clustering will start. And now the algorithm with all points gray. Now suppose we know that k equal to 3. Now I will come to this point later, that of course you can't know for exact how many clusters are there in the data set, but you can get some idea about how to set the value of k, that I will come to later. But as of now, let's just say that somebody has come and told you that k equal to 3. So if you go through the k-means algorithm, it will first randomly select 3 points. So suppose it selected the first 3 points like this. It decided the blue cluster, the yellow cluster, and the green cluster, and then they assign all the so these are the cluster centers, because they have got the first points, so they are themselves the cluster centers. And then what they do is they assign all other points based on the distance from the cluster centers. So you can imagine that blue will only be assigned to this, yellow will be only assigned to this, while all of these will be assigned to green, because all these 4 points which are gray in this particular figure are farther from yellow and blue as compared to green, so all of them distance wise will be assigned to the green cluster. Okay, any doubts anywhere, you can stop and ask me. Okay, I will go ahead if you don't ask me any doubts. Right, so once you do that, then the next step of k-means is you need to find out the means of all the 3 clusters again. So blue has only 1 point, therefore blue will have a mean of 1. Yellow has only 1 point, so yellow will also have a mean of 2, and these 5 green points, if you add 5 plus 6 plus 9 plus 10 plus 11, you would see that it comes out to 8.2. So the green cluster is somewhere, if this is 6 and this is 9, then it is somewhere here, let's say. So this is suppose the green mean, if I may call that. Okay, now you calculate all the points from the individual cluster means. So of course point 1, it is blue and it is nearest to the blue cluster because the distance is 0. The distance of this point 1 from the blue cluster is 0, because it is the only point that is there in the blue cluster. Similarly, point 2 is nearest to the yellow cluster because there is only 1 point and the cluster and the distance is also 0. The point 3 distance from the yellow, now let's come to this point. Now the cluster center, the blue cluster center is at 8.2 and the yellow cluster center is at 2 and this point is actually at 5. So, you see what is happening is it is actually closer to the yellow cluster as compared to the green cluster, because this distance is 3.2 and this distance is just 3. Therefore, the distance from the yellow cluster is 3, distance from the green cluster is 3.2, the nearest cluster is yellow. After this, all the points from from the 4th point onwards, all the points are closer to the 8.2 and therefore, all of them will now be assigned to the green cluster. So, this becomes a green cluster, this becomes the yellow cluster and this remains the blue cluster. Okay. Is this clear till now?
Yes, sir.
Okay. Then after this again so I am just going through the different iterations of k-means algorithm. It's the same thing again and again you have to do. So after this again you calculate the cluster means. Now blue again won't change, but yellow will now change to 3.5. So yellow is 2 plus 5, so it is somewhere near here, it's 3.5 and right. So this is 3.5, let's say, and green is 9, it changes from, so if you add all these 6, 9, 10, 11, so it is now at here. So this is the green cluster, this is the blue cluster. Now you assign all the points, you see blue is the first point will still be assigned to blue, the second point which is at 2 is actually closer to the cluster mean of 1 than to the cluster mean of 3.5, and therefore 2 is now assigned to the blue cluster. And if you do it and if you carry on this procedure, you will see that 5 and 6, I mean the third and the fourth points which are at points 5 and 6 will now be assigned to the yellow cluster, and the last 3 points will be assigned to the green cluster, and that is what you basically want. I mean when you had looked at the point, you had looked at this just without any cluster, without any colors, you would have also found out these 3 clusters and compute the means. The mean now after as reassignment of the points, blue will be 1.5, yellow will be 5.5 and green will be 10. Reassign the points again, because you do not know in k-means clustering whether the points that you have found are actually good or not. So you continue doing the same algorithm and you calculate the means, and you will see that the means won't change, which means that the k-means algorithm has converged. Okay, so that is the stoppage of k-means algorithm. So you started with completely unseen colors, and with by means of the k-means algorithm, a very simple algorithm, you ended up with this clustering, which is perfect in this case. Now people often say that k-means algorithm is very susceptible to the starting point. Now let's see that what can happen if you have a bad starting point. Now suppose in the first case I had considered these 3 as a starting point. Now let's say you consider these 3 as the starting point. It's quite possible that you select 3 points, the last 3 points as your 3 starting centers, cluster centers. So once you do that, you will see that the initial so here the yellow and the green cluster will be assigned to 1 points only, all of them will be assigned to the blue cluster. Okay. So after this, the mean of blue will be at 5.6, which is here, and yellow will be here and green will be here. These are, I mean, the lines that I am drawing are the cluster centers, and based on the distances the reassignment will work as follows. So after you reassign, all of these will become the blue cluster, these 2 will become the yellow cluster, and this will become the green cluster. And you can continue doing the k-means algorithm, you will see that this assignment won't change. Okay. So depending on whatever k you start with, you might end up with completely different clusters. Okay. So what is generally followed is you generally what happens is I mean these 2 particular clusterings were clusters which we got from 2 different starting points of the k-means algorithm. They actually might not be, I mean to us with this simple example it might seem that okay, k-means algorithm may do completely poorly in case of certain starting points. However, in general, in practice, k-means algorithm doesn't seem to work that poorly. The other thing is you generally run k-means with a large number of starting points. okay, and there are different ways of understanding how pure is your cluster, how pure is your clustering. So how good is your clustering? So a goodness index of clustering can always be defined, and depending on that you can stick with one set of clusters or go with another set of clusters. Okay, so the takeaway from all this is, for k-means algorithm, since it depends so much on the starting points, it's better to run with multiple starting points and see which gives me a better clustering algorithm. Generally if your data set is suitable for k-means algorithm, then most of the starting points will give you good enough results. Okay, so that is one thing that I wanted to mention. And okay, so the other thing which the thing that I told you about, that how will you understand which clustering is a better clustering, which starting point is better. So this is the clustering that you got when you started with the bad initialization, and this is the perfect initialization, right? Now let's see. So with two different starting points, we have got two different results. No way to know which is better, but is it actually true? Now one thing which we can always do is, we know that this all belongs to one class, this belongs to one class, and this belongs to another class, right? So I am computing the variance of the blue class in the first example. So if you see here, 1 plus 2 is 3 plus 5, right. So the center of this would be 3.5, the blue mean would be 3.5, okay, and this is the variance. So 1 minus 3.5 whole square plus 2 minus 3.5, 2 minus 3.5 whole square plus 5 minus 3.5 whole square plus 6 minus 3.5 whole square, all of this summed will give you 17. Okay, so this is the variance of the cluster with which has all the blue points in it. Okay, the variance of the yellow cluster, you can calculate, it will come out to be 0.25. What is the green class variance in the first case? Can somebody say?
0, sir.
Yeah, it is 0 because there is only one point, so that is why there is no variance in the green class. So if you add the variance across all the three classes, you see that in the first case the variance comes out to be 17.5, 17 for the blue class, 0.5 for the yellow class, and 0 for the green class, and therefore it comes out to be 17.5. Now let's compute the same thing for the second clustering. For the second clustering, this 1 and 2, it will be 0.5, yellow again it will be 0.5, I am writing the variances here, and 9, 10 and 11 it will be 2. So this will so the green class has a variance of 2, the yellow class has a variance of 0.5, and the blue class has a variance of 2. So in total the variance is 3. So what does this variance mean? So this variance means that although I have assigned all these 4 points in one cluster, they are widely spread out. It is not like they are very close together in that particular cluster, they are widely spread out, and because they are widely spread out, that is why the variance has come out to be quite high. And since the variance has come out to be quite high, I can say with confidence that the points are widely separated out on the x-axis and in the same cluster, and therefore that is not a very good cluster assignment. So whenever you have two competing cluster assignments, you calculate the total class variance, and whichever cluster assignment gives you a lower variance, you consider that to be the better cluster. Hence in this case you can conclude that the second assignment is actually better, the second cluster assignment is actually better. Is it clear to everybody, this point?
Sir, along with that variance within the cluster, we have to also consider the distance between the clusters, right, sir?
Between the clusters also you can consider, but in this case variance within the cluster itself is yeah. So what the thing that you are saying is the distance between the two clusters. The distance between two clusters, if you consider, that means the clusters are widely separated from each other. Okay, so that so for finding out two cluster assignments, I think this in most cases should suffice. Yes.
Okay, sir.
Yeah. Right. Okay. So so the next question comes is, how about selecting the value of k? So that is one thing that is always I mean, you started with k, right? I mean, you saw that k was equal to 3, that is why you randomly selected 3 points, but who gives you that k? That is the other point that you want to mention, that you want to see, right? So here you see what you will do is, you will start with k equal to 1. So this is the general way in which k-means algorithm will generally proceed. So you will start with k equal to 1. That means all of them are belonging to the same cluster. You calculate the variance of that. Okay, that is the first. Then you do k equal to 2. Suppose by some cluster assignment you got some initialization, you got this cluster, and the variance of that comes down to 19. I mean, by variance here I mean that you calculate the variance of each class and add them up. Okay, then you got k equal to 3, and for 3 you got k equal to 3 again. Okay, then you took k equal to 4, you got 4 clusters. Now your cluster total variance comes down to 1.5. Okay, now can somebody tell me what will happen if I take k equal to 7? What will be the variance if I take k equal to 7?
0, sir? 0.
Yes, it will again be 0, because all of the points will now become their own cluster centers. Okay, so you have got this particular thing, 91.43, 19, 3, 4, 1.5 and 0 finally for 7. So what you need to do is, you need to plot them on the the variance versus k. So for 1 you had 91 point something, for 2 you had come down to 19, for 3 you had come down to something, and for 4 again you go down. Okay, so here what you can do is, now this, whenever this curve comes, there is something which is known as the people call it the elbow method, some people also call it the knee method. So I generally knew that it was always the elbow method. So the elbow method tells you that, okay, at this, for example here if you see, at k equal to 2 there is a large drop in, I mean from k equal to 1 to 2 there is a large drop in variance. From k equal to 2 to 3 there is, okay, not that large a drop, but there is still a drop. From 3 to 4 the drop is not that much. So this looks like an elbow. I mean, so why is it called the elbow? Because this or this can be the joint of your elbow, right? And so this is basically your arm, and this is your, I mean, this is your elbow. I mean, this is the elbow joint. You can consider that, that your hand is facing like this, and this becomes your elbow joint. And whenever there is a sharp change in slope, so here there is a sharp change in slope, and that is why this can be considered as a joint. And because of the sharp change in slope, you can see that, okay, if I increase the value of k after this point, that means my variance is not reducing that much. So I better take k equal to 2 in this case. Okay, is it clear? I mean, this is a very empirical thing to see, but this is the way to choose k. Is it clear?
Sir,
yeah.
Sometimes that is tricky, there are 2 and 3.
Right, it is tricky, I understand, but that is the way it is. I mean, you can only select k in this ways. Okay,
so we start from 1, and highest fall, that is the one we take.
Not the highest fall. I mean, so sometimes I mean, generally this is a very simple example. Generally what will happen is, it will be like this, okay. I mean, I hope my drawing is clear.
Yes.
So it will fall down like this, then it will go like this, then it might go like this. So in this case you will take this as your elbow value, because you see this is a large drop. Okay, then it will again start going like this. So, so you have to see the curve and understand that, okay, I mean, for example, when you will draw this curve, always you will see two competing points. You can select any of them. For example, here you could see that 2 is a good point, 3 is also a very good point. You could select any of them. Okay. So, what is 2 and 3? Yeah, 2, see, 2 is this point, 2 is this clustering, and 3 is this clustering. So, suppose somebody had come and told you that there were 2 clusters, you would have probably got these clusters yourselves. Somebody had come and told you there were 3 clusters, you would have got these 3 clusters yourselves. But this clustering is not as bad as this clustering, I mean, is not very bad as compared to this clustering. This is still good, this will work. Okay. So, this will still work. That is what I am saying, that this 2, 3, 4, I mean, all these values they are very subjective. Also there are just what, there are just 7 points in this case. For clustering you will generally have in the range of 10,000 points or something, then the drop won't be as sharp. Okay, you would probably see a very clear elbow in that case. But
from 2 to 3,
yeah,
the drop is still significant only, right?
it's
sir?
still
Not
significant.
like flat.
Yeah, it's still significant. It's just that from the curve, if you see, this slope, the change in slope is much higher, looks much higher here. Okay, it is I mean, I am saying that from 3 to 1.5, the difference that you have, the difference in 19 to I mean 91, I mean this is 91, this is 19, and this is 3. So this, it looks like me that the change in slope is much more at this particular point than at this point. Okay. So of course you are correct that 19 to 3 is still a big drop, but I am saying that you have to eyeball this and get your measurements and get your results. I mean, this is just this is just a very empirical way of setting k, and this is the only way that we can set k ideally. But you have to look at it and understand. Yeah.
Sir, that variance means we have to add up variance of individual clusters.
Yes.
So if you have 5 clusters,
Yeah.
calculate variance of each cluster and then add up all that.
Add up all of them. Yes. So, so the way to set k is, as I said, you start with k equal to 1. Of course, that will be the worst. Then you go up to k equal to 2, 3, 4, 5, 6, 7, whatever, and you draw all these variances, and then you eyeball this diagram. And whenever you feel that, okay, the slope is more or less, it looks like an elbow at this point, it looks like a joint at this point, I will take that as my k value and run my k-means algorithm with that k. Okay.
Sir,
Yeah.
Sir, another performance is inter-cluster distance also is an indication, right? That inter-cluster.
Intercluster, yeah, there are different ways to find out. The particular, I mean, to understand what is a good clustering and what is not. Variance is one direction. The thing that you said is also one. There are many other ways also. Okay. So yeah, there is something known as mutual information, that is also there. Some correlation is there, some correlation based measures are also there. This is a very simple measure and this works just fine. Okay, so that is about k-means clustering. It's a very simple algorithm, but it's very effective. Okay, then we come to hierarchical clustering. So it's a so I will be talking about agglomerative hierarchical clustering. It creates a structure which is known as dendrograms. Okay, so I have taken this example from this particular link. So let me go through an example one by one. So suppose you have n clusters, so you have n data points. So for n data points you will have n clusters, so all of them are different clusters in this case. Okay, so take the closest data point and merge them into a single cluster. Okay, so you take the closest data points and you merge them into a single cluster. That's the first thing that you will do. Okay, for n data points there will now be n minus 1 clusters.
Sir,
Yeah.
to do that first we take each point and calculate distance from that point to all other
All other points here, yes.
And whichever is the nearest, that one you make
Yes.
2 points, 1 cluster. And for the next point, when we choose, we have to choose from the n minus 2, right?
N minus 2 means?
Means the first 2 points we formed a cluster. That
Yes.
is over.
Yes. I'll come to that. I'll come to that. Yeah.
Okay.
Yeah. So this is a first cluster that you have formed. Now you continue doing so until you have got one big cluster. Okay. So suppose the first 2 points were here, then okay, I will come to the point about how to decide on the distance between a point and a cluster. Okay. So I'll come to that. Just a minute. So I'll come to that. So this is probably one way of, I mean, somehow somebody comes and does the hierarchical clustering for you. So what you will do is you will take these 2 points, then you will get one cluster, then you select these 2 points. Suppose these are the closest points, that's what I'm assuming right now. After that you come here, then
No, sir.
Yeah.
We understand graphically,
Yeah.
but programmatically, how you do. So let us say we got 100 points, okay?
right,
So first is we have to find 2 pairs, right? At the bottom most we have to start with the 2 pairs, correct?
2 base means
2 means a cluster of 2s, 2 points. 2
yeah.
closest.
Yeah.
So out of 100, we have to form a cluster of 50 clusters of 2 points each.
No.
Not like that.
No. So what will happen is, if you have, let's say 100 points, okay, if you have 100 points, you will create a matrix of 100 cross 100,
Yes.
and all of these diagonal entries would be 0. Okay, all of these diagonal entries will be 0, and it will be a symmetric matrix. So you will calculate the distances between the first point and all the other 99 points, then the second point and all the other 99 points, and so on,
Yes.
and you will keep this matrix as it is.
Yes.
Then you take the minimum value of this matrix. Within this matrix you take the minimum value, and suppose that minimum value is at the point ij, the ith row and the jth column of the matrix, right? So once you take that, that means that out of all the points, I and j are the closest points.
Yes.
So you merge I and j into one cluster.
Yes.
Then you again go back to the matrix. Now we have already merged I and j,
Yes.
right? So now what you need to do is you need to go and so I and j will now become a single point. They are part of one cluster,
Yes.
right? So if you are so now I think if you have gone through the lecture, there are different ways of computing the distance between a point and a cluster. So depending on that, if you do a complete linkage, if you do a single linkage, if
Maybe those 2 points are to compute h, and not like that.
huh,
No, those 2 points, the closest points,
right,
we have to compute the centroid of those 2 closest points, right? That 2-point cluster.
no, I mean that means you are doing a centroid linkage. Suppose somebody comes and tells you have to do single linkage, then you can't replace the 2 points by the centroid.
Yeah, just please explain the single.
Yeah. So let me come to that in some time. Okay. But before that, okay, let me go through. So single linkage I will come to, but let's go through what the dendrogram represents, or maybe I will first look at the single linkage only. Okay. So distance between points. So the first point is distance between points can be the Euclidean distances or any other distance metric that we wish. That is our wish. Okay. However, distance between the clusters.
Many times, right, when we see about k-means, they always tell Euclidean distance is preferred over Manhattan distance.
Right.
So any reason, sir, why for k-means Euclidean is preferred than Manhattan?
That is actually a very deep result. Actually, you see, I mean, in the what can I say? In the lecture, if you remember, towards the end, the professor had actually mentioned something about EM algorithm, right?
Yes, sir.
So she had said that k-means algorithm is actually a very special case of EM algorithm, and EM algorithm actually is used for solving something known as Gaussian mixture models. So okay, in short, what can I can say this, that K-means algorithm assumes, it is always assumed in K-means algorithm that the data that is coming to you is distributed according to a Gaussian. Okay, and if you see in the so if you now if you try solving the EM algorithm with a Gaussian with the assumption that your data is actually Gaussian, then that L2 distance or the Euclidean distance comes as a result of that EM algorithm. Okay, so that is why K-means is generally always followed with Euclidean distances. It is generally never done with L1 distance. I don't know whether I made sense, but you can understand that K-means algorithm always thinks of your data to be distributed as a Gaussian, and because it is always considered to be distributed as a Gaussian, you are taking the L2 distance than the L1 distance.
Okay, and it doesn't depend upon the dimensions.
No. Okay, so hierarchical clustering. So yeah, single linkage and the distance between the 2 points in the cluster. So what will happen is, suppose you have 2 clusters, this is your cluster 1, this is your cluster 2. Single linkage means you will take the distance between all these points and all these. So suppose there are m points here and n points here, you will compute all these m into n distances, and you will take the one which is the smallest. Okay, so if 2 points in a particular cluster are very close to each other, then that will be assigned as the distance between the 2 clusters. Okay, that is single linkage, and complete linkage is the exact opposite of that. You take the distance between the 2 farthest points of the clusters. So single linkage was here, farthest linkage is here, complete linkage is here. You take the 2 farthest points and you take that as and you assign that as the distance between 2 clusters. Okay, and then you have the centroid linkage. That is quite simple. You take the midpoint of all of them and you compute the distance between them. There is another thing known as average linkage I saw, but average linkage is rarely used. So these 3 are the most widely used linkages, and average linkage is basically the average of the distances between all the points. So that is
centroid and average not the same, sir, because centroid also it finds the average between all the points in that cluster, right?
Actually, centroid.
No, it is not the same actually.
Sir, as I understand, please correct me.
Yeah.
Centroid means all the points are xi I is equal to 1 to n divided by 2 sigma of yi is equal to 1 to n divided by 2. Correct? Centroid.
Yeah, I did not get that sigma, all those things. I'll write it here. Okay, this is the centroid linkage, and
is it minus, sir, in between x square and
That is
yeah,
that's not minus. That
yeah,
is
yeah.
That is minus.
Yeah,
No.
you take the 2 centroid and you take the difference between them. Okay, and that is and the other is this, sorry,
X is a x dimension, x coordinate, or what?
no, I am talking about 2 clusters. Okay,
Cluster. X is one cluster, Y is another cluster.
yes, x1, x2, x3 are the 3 points in one cluster, y1, y2, y3 are the 3 points in the other cluster.
So basically they are vectors, x1, x2, x3 are vectors.
Yeah, you can consider them as vectors, you might not consider them as vectors, doesn't matter. Yeah, so x1 minus y1, so this is right, okay, plus x, right, okay. Why is this happening?
No, the distance is
Yeah,
x1 x minus y whole square.
What is x?
No. See, x is a point, is a vector of 2 dimensions, right?
Consider x as a scalar, okay? Consider x as a scalar where x1, x2, x3, I have not written x anywhere. x1, x2, x3 are 3 points in one cluster, y1, y2, y3.
We are getting confused. We are looking at 2-dimensional geometry. That definition of suppose, let us say, go to high school geometry, just to 2 coordinates x and y, plane geometry.
That will be difficult to write also, right?
Yeah. So here,
Okay.
here x means all points belonging to that cluster. Y means all points belonging to that cluster.
Let me write in the way which you would understand then. Okay. Right. So this is x. This is cluster. This has 3 points x1, x2, x3. This is y. This has 3 points y1, y2, y3. These are my 2 clusters x, y.
My only question is, when you say points, the data, the point can be any dimensional vector.
Right, like this point. Okay, like this point. Yeah. So what I am trying to say is, what is the centroid of x? The centroid of x would be x1 plus x2 plus x3 by 3. What is the centroid of y? This is x1, y1 plus y2 plus y3 by 3, right?
Yes.
So x hat my x bar minus y hat transpose xy minus y hat. This is the distance between the 2 points, okay, the 2 centroids. This is the so is this notation clear?
Yes.
Okay.
Nothing but Pythagoras distance between x square plus y square. Yes.
Right. So that is the distance between the two vectors, and that is the centroid that is a centroid linkage. Okay, this is the distance between the 2 centroids, right? And
Distance square.
distance and distance square, both of them are more or less similar. Okay.
But the equation is distance square, right?
Right. Yeah. The other way is you calculate for every point, you calculate the distance from all the points in the other cluster, and you add them up, and then you divide by the and then you average them over the total number of points across clusters.
The question is, don't come the same point, same
No,
thing?
no, they won't come to the same thing. You can check yourself, or with a simple example it won't come to the same thing. Okay. Right. Yeah.
What is for the average, sir? For average, what will be the?
The average is this one. Average is this one. You take the centroid of the 2 points and you get the distance between them.
Right, but no, for average linkage means.
Oh, this is a centroid linkage. The average linkage, you take 1 point, then you calculate the distance. For example, you take this point, you calculate the distance between this point and all the other points in the other cluster, and you add them up. Then you take this point, you add up all the distances with again all the other points in this cluster, then you add them up, and in this way you add all of them up and divide by the total number of points across clusters. Okay, so but generally that is never used. So centroid linkage and single linkage and complete linkage, these 3 are the only things generally used. Okay, so
when you just start, right, sir, in the first step.
Yes, first step.
Right.
Yeah.
If you can go little above.
Right. Yeah. Here.
Yes, here.
Yeah.
So if we use complete linkage.
No, complete linkage doesn't come into play when all of your, I mean, yeah, continue your question. I will come to the.
So single linkage I can understand, sir. First find nearest and then first find the first cluster. But in complete linkage we always find the farthest points for that cluster. How does it work as a first step is what is not clear for me for the complete linkage.
Actually, sir, the complete linkage length is more than the single linkage, correct?
Yes. Yeah, so the first thing.
Is my question clear, sir?
Yeah, I got your question. Let me think. Okay, complete linkage. Take closest data points and merge them into a single cluster.
Actually, sir, it's only three concepts. Either you take the left one extreme, two extremes are in the middle average. Only three ways of measuring the distance.
Yeah. So complete linkage. No, I think your question is good. I mean, I think for the when you are starting, you will always start with the closest data point. Okay, when you are starting, you will always start with the closest data point. When you will think about merging a point with a cluster, the distance between that point and that cluster will be taken as the complete linkage or the single linkage or centroid linkage.
Okay, so in that case, the first cluster will always be single link, and later on all the further ones will be complete linkage in case if it is a complete linkage.
Yes. Okay, so that is single linkage, then there is complete linkage, then there is single linkage. Okay, now let me come to the dendrogram. So here what happens is so here suppose you have some 6 points, I mean some 6 points here. So somebody, you have gone through some distance measures, you have taken some complete linkage, something or the other you have taken, and suppose P2 and P3 was found to be the closest points. Closest points in terms of distance, that means the distance between P2 and P3 was the smallest, and you took that and you first you merged them. Okay, that is the first merging that you got. After that, the next merging that you got was of P5 and P6. So somebody, I mean all those distances somebody is computing for you and telling you which is the closest points, and then you merge P5 P6. Then somehow I think that these two clusters are more or less looking very similar to me.
Sir, one fundamental question.
Yeah.
Here the notation index we are using P1 to P6, that is why we are able to write the side by side.
Yeah.
The x-axis, in fact P1 to P6 we have to discover, right, what is the correct order with reference to what point.
Yeah, somebody is doing that for you.
Let us say 6 points randomly given to us.
Yeah.
First we have to sort out with reference to any one point what is the order, higher, lower. So
which one?
See, in the dendrogram the assumption is P2 is nearer to P1, P3 is nearer to P2. No.
That is. I mean, no. See, this. How can I say? See, this P1, P2, P3, P4, P5, P6, right?
Are not random, they are sorted.
No, they are not sorted. This might be point number 11 in your data point. This might be point number 1. This might be point number 3. This might be point number 4. This might be point number 100. This might be point number 88. Doesn't matter. Okay. There doesn't. I mean, this P1, P2, P3. They can be any random set of numbers. It's not like P1, P2, P3, P4, P5. They are just for ease of explanation of the diagram.
Okay, sir.
Right. So P2, P3 can be any random points. Okay. So yeah. So 1 and 3 they were the closest. After that P5 and P6 are the closest. Then this appears very similar to me, but anyway, okay. Suppose these two distances are very close. I mean P2, P3, this cluster, and the distance between P1 and P2, P3, and the distance between P4 and the cluster of P5, P6, probably these are very close to one another, and you merge both of them, and finally you merge all of them to reach a single point. Okay. So this is the dendrogram. I mean, after all this, you create something which is known as the dendrogram. I mean, you have also seen one such example in the lecture. Now for this, what happens is, what does this give you? Why do you want a dendrogram in the first place? Now see, here the first thing is dendrogram actually. So what was the major issue with k-means algorithm? The major issue with k-means algorithm was to set the value of k, right? here in some sense you are actually getting a sense of what the value of k is, okay, which value of k you should take to get a good cluster. I will come to that example. I will come to another example in a bit that will be make it more clearer. So suppose if I cut the dendrogram at this point, that means I have got one cluster here, I have got one cluster here. That means all these 3 points are cluster 1, all these 3 points are cluster 2. If I cut the dendrogram at this point, that means I have got 4 clusters, this one, this one, this one and this one. So that means P2, P3 become one cluster, P1 is one cluster, P4 is one cluster and P5, P6 is one cluster. Okay, so how many vertical limbs of the dendrogram you cut when you cut it at a particular point, those many number of clusters you will get from your data set. Okay, so after clustering. So now how to decide where to cut? So let me come to this example. Now you see this is a big complicated diagram with many such so the dendrogram is quite complicated here. Okay, so now there are 4 possible arrows I have drawn here, 1, 2, 3 and 4, where you can cut the dendrogram. So okay, first without asking let me ask you, without asking the actual question, let me ask you, suppose if I cut the dendrogram in this small rectangle of 1, how many clusters will I get?
1.
2, sir.
It will be 2, right? We are, as I said, you will always, whenever you I mean the number of vertical limbs of the dendrogram that you intersect, those many number of clusters you will get. So you are cutting in between, so I mean cutting in this rectangle of 1, that is why you will get 2 clusters. Now can you say that is this clustering good? I have not told you anything, but can you tell me, can you give me an idea about what should I look at if I have to understand that my clustering is good or bad from a dendrogram?
The inter-cluster distance should be more.
Inter-cluster distance should be more. So is this a good clustering or not? I mean if I cut it at 1. I mean these are all relative, right? Suppose if I cut it at 2, is 2 a better cutting point? Somewhere in the rectangle 2, is it a better cutting point, or somewhere in the rectangle 1, is it a better cutting point?
So when you cut at 2, we get 3 clusters.
Right, right.
So the question is whether 2 is better or 3 is better.
No, I am not talking about number of clusters. I am talking about when you get 2 clusters, when you cut it through 1, is that better than when you cut it at 2?
2 is better, sir.
Okay, why?
Because from that y-axis we see that Euclidean distance between both clusters is very small. It's the distance when we cut at 1,
Right.
that distance is very minute. It doesn't mean like they are both separate clusters, but whereas if I cut at 2,
Right.
so I can see that the distance
Right.
is the distance inter-cluster distance is more if I cut it at 2.
Is it clear to everybody? I mean
Sir, that y-axis Euclidean distance is intra-cluster or inter-cluster distance? Y-axis, can you explain y-axis?
y-axis doesn't have any intercluster or intercluster distance mentioned. It is just Euclidean distance.
Distance between what?
You tell me. What is this distance? For example,
The distance between that blue clusters
And
points
the red cluster.
First clusters.
yes, yes, precisely. So this is basically the intercluster. Right. Okay. So I mean the explanation which I don't know somebody gave, right? That was very good. Okay. See, so what is happening is whenever you merge the dendrogram one cluster with the other, the distance is always plotted on the y-axis. So that means when you had merged this cluster with this cluster, the distance between these two clusters, whatever complete linkage, single linkage, whatever distance metric you had chosen, that came out to be this particular value. That is why you merged them and you put this bar at this particular value. Okay. So that is the first point. Okay. So now that is clear, if that is clear, that means that if I am it's very difficult to draw also. Okay, if I am doing something like this, if I am cutting it within the rectangle of 1, that means I am getting two clusters. All of these points are becoming one cluster and all of these points are becoming one cluster. However, the distance between them is just this much. Is it clear?
Yes. It's very big distance.
It's a very small distance.
Very small.
Yeah, it's only this much, which means that the two clusters are basically not different that much. They are more or less similar. So why will I cluster it in the first place? My entire point of clustering was to partition my data into groups such that all the groups are dissimilar among themselves. If I am getting two clusters which are very close to one another, then I shouldn't have clustered in the first place. Doesn't make any sense to cluster. However, if you see, if I cut here, that means that there are three clusters. One of them is this. Okay, I will rub these, and one of them is this, the other is this, the red ones, and the other is the blue ones. Okay. So if that is the case, that means that okay, the blue ones and the red ones will have much higher distance. You can calculate them. The blue ones and the red ones will have a much higher distance, and the blue and the red and the blue, they already have this computed distance. So all of them are more or less quite different from each other. So it's good to do a clustering at 2. I mean, you will get these three clusters basically. That is one possibility. The other possibility is if you cut it at 4, that is also okay, that is not bad. But the best way, of course, would be, as has been shown in this diagram also, the best way to cluster would be putting it into the green blocks, the blue blocks and the red blocks. So that is the utility of a dendrogram. You can just look at the dendrogram. So there are, of course, you don't have to draw the dendrogram yourself. Python will have packages which can give you the dendrogram. Once you look at the dendrogram, you can just look at the dendrogram and see that okay, if I cut it here, then it's the best. Python will also tell you where to cut, because of course they will compute everything and tell you everything, but that is the way Python will work. It will look at the distances and it will say okay, if you cut at this particular point, you will get three clusters which are sufficiently different from each other. Okay, I hope that was clear. Okay. Okay, so now let me ask you this question. Okay, so I hope the distances are clear to you. This was actually given in this course last year's or previous to last year's assignment, I am not sure. Okay. So here what you are supposed to say is, you are supposed to say which one is a single linkage, which one is not which one is a single linkage between these two clusterings. Okay, don't need to look at the dendrogram, you just need to look at what is happening in these two clusters. These clusters are given to you, and the ordering is also given by means of this red numbers. Okay, so you see here. So as I said, you first compute these matrices. So this is there are 6 points in this matrix, so you will compute a 6 cross 6 matrix and you will compute the minimum value between all of them. So you see that the minimum value between all of these values in the matrix would be between 3 and 6, which is 0.11. This is the minimum value. So the first cluster that you get is 3 and 6. Okay. Then the second cluster that you will get is after 3 and 6, the next value would be 0.1388. So you just need to look at the matrix very carefully, and then the next cluster will be formed, which is 1 2 and 3 6. The first cluster that is formed is 3 6, the second cluster that is formed is 2 and 5, the points 2 and 5. Right. So, for both these diagrams 1 and the 2, this ordering is the same. Then the third cluster in the first diagram appears between, it merges 5 2 3 6 into 1, you see here, and the second diagram it merges 3 6 and 4 into 1. So, one of them will be a single linkage. So, let us look at it. Now, if you look at 3 6 and 5 2, if you are doing single linkage, then you see that the distance between 5 2 and 3 6 would be 0.1483, which is the distance between 2 and 3. Is it clear to everybody?
Yes, sir.
Yeah, these are the two closest points between these two clusters. Okay, and let us say you take 3 6 and you take 4. So, you take 3 6 and you take 4 3, okay, you take 4 and you compute the distance between 4 and 3, that is 0.1583. You compute the distance between 4 and 6, which is 0.2216. So, 4 is farther than 3 6, 4 is farther than 3 6 than the cluster of 5 2 and 3 6. Is it clear?
Yes, sir.
So, that is why this one would be the single linkage one, because for single linkage you will always take the distance between 5 2 3 6, compute that to be 0.1483, and that becomes your smallest distance, and therefore 5 2 3 6 becomes your single cluster. So, this is a single linkage one. Okay, I hope this.
Sir,
Yeah.
just one question. Okay, I understand single linkage.
Yeah.
But how to arrive at the bottom diagram? Okay, first, please explain the procedure. First, we have to make the table, cross linkage P1 to P6 versus P1 to P6, compute the distances, and then first look for the smallest pair. So,
right.
The smallest pair we found is 3, 6. So, we
right.
have to call that as a cluster.
Right.
And then the nearest to that next nearest to is 0.1388, which is nearest to 3, 6.
Right. Right.
Okay, that is
no, 0.1388 again you take from the matrix. The 1388, the next value that comes out to be is 1.1388, and that means you have to merge points 2 and 5, and that becomes your second cluster.
Oh, 2 and 5. Okay, how do we know to merge 2 and 5?
Because that is the smallest distance, no?
Oh, next smallest.
Next smallest distance. Yeah. Then you see that I mean, if you go through this matrix, then the next smallest value is 0.1483.
Yes.
So yeah, so that is how you.
That is.
Yeah.
Yeah, 0.1483 is between P2 and P3.
Yes. Yes.
Okay.
I mean, how you got this bottom diagram is up to you. I mean, that somebody might have done centroid linkage also. That I would require more calculations to prove. Somebody might have done complete linkage. Somebody might have done average linkage. Single linkage, complete linkage, they will be generally easier to see.
Okay.
Okay. So.
Sorry, sir, I couldn't understand your last sentence. Which diagram is difficult?
I mean, this one. I mean, I don't know, for example, how this diagram is created. I mean, which linkage will lead to this particular diagram? Probably complete linkage. I don't know.
In complete linkage, we will take the maximum value.
Maximum value. Yeah, I don't think that is complete linkage also.
In complete, we take max. No?
Yes. In complete linkage, you will take maximum value. So it's difficult to say which one will. I mean, what diagram this comes from. It's. I mean, single linkage is easy to see.
I'm asking in the process, like in single linkage, we take the minimum.
Yeah. Single linkage, you will take minimum.
In the even first pair, we will choose the highest value.
No. First pair, you will always choose the lowest value.
Minimum.
Yeah. Then whenever you have clusters, you are forming clusters and you are trying to compute, there you will take the max. Yeah.
sir, I'm looking at the problem. Let us say an exam, a problem is given.
Yeah.
The top coordinates are given. P1 to P6, X and Y is
Right,
given.
right.
And say using single linkage
Huh.
from hierarchical clustering.
Yes.
Okay. We
Huh.
don't know anything.
Then the first thing that you will have to do is to create this matrix.
Yes. Then.
Then you go about seeing which is the minimum value.
Okay.
So what is the minimum value? You merge them first. Then you take the next minimum value and go on.
Yeah. So to 2 we'll be merging actually 2 pairs.
2 pairs. Yes. Yes.
Yeah. Yeah. 2 pairs only will. See, that's what my confusion is. For me, it is very easy to identify pairs by sorting looking at the table.
Yeah.
I can say all the pairs I can close
Yeah.
pairs. And the closed pairs I call it as a 2-point cluster. So I can make ellipses around all the 2 points. And then 2 points should be matched with. Okay.
No, the only thing that you have to remember is whenever you are matching a point or whenever you are trying to find out the distance between 2 clusters, you will always need to follow that complete linkage, single linkage, whatever. And that is the only thing that you need to. It will require a bit of bookkeeping, but apart from that, it is not very complicated. Also, you will need to do a little bookkeeping. Yeah, that's the only complication here.
Okay, sir.
Okay, so
one more doubt. In dendrogram, some leaves are not linked. Then do we consider as a cluster? Actually, somewhere they don't count them as a cluster. They given some other name.
Which one? Which dendrogram?
In dendrogram, suppose there is a few leaves. Leaves are not connected. We directly add to the root.
Dendrograms.
One case. Yes.
Which one?
In this case, no. Here all the are linked.
No, you can link all of them. You should link all of them.
Yeah, we have to connect all the points. We
You
should not leave any point.
You shouldn't leave out any point.
It directly go to the up. I think some outlier points.
That is fine. That is fine.
We consider as a cluster or not? That's the question. Conceptual question.
I mean, you are saying that if you have a single point and all of them will become a single cluster. No, you shouldn't consider that. You shouldn't.
Those leaves are connected directly to the top. And they are outlier points.
If they are outlier points, then you shouldn't consider. But suppose there is 1 point. Okay. Suppose there is 1 point here, and you are saying that it is connected. There is a single point here, and it is connected something like this. Okay. So you should not consider. You should not consider.
There are cases,
Yeah.
Where it is not considered, but in our example in the lecture, they have considered as a cluster. That's
Okay. You should. I mean, for all practical purposes, if there is a single point in one cluster, if 1,000 points in the other cluster, you should never consider that. Okay, so this is done. Now let me, very simple questions only. So there are 4 questions or 3 questions only. Okay. So the hierarchical clustering, I think the question that I have given is more or less sufficient. So so these are also very simple questions. So for 2 runs of k-means algorithm, as we saw, for 2 runs of the k-means algorithm, we generally is it expected to get same clustering results? So in most cases you won't get the same clustering results. Okay, it will differ depending on your starting point, because always remember that k-means clustering algorithm will generally be done when you have thousands and thousands of points, and all the points being assigned to the same cluster center every time you run. It will never happen. Okay, so
Actually, convergence takes a lot of iterations, correct? Many runs.
Not necessarily. Convergence can be pretty fast also. If k-means is not converging very fast, that means k-means, that also gives you an indication that your value of choice of k is probably not correct. Okay, so if it's probably lower, you have to increase it. Might be. might be, we don't know for sure, but
so here we are saying that we don't get same results. That is because of the initial points.
Initial points, yes, precisely.
So if initial points are same, it should get the same result.
It should always give the same result, yes.
Okay.
Right. So the other thing is it possible that assignment of observation to clusters does not change between successive iterations? Yes, it is possible. When the k-means algorithm has converged, it won't change. It won't change between successive iterations of k-means. Okay, so and the last question is, which of the following algorithms suffer from the convergence at local minima? So k-means will always suffer from that, and expectation minimization clustering was referred to very briefly in the course. So I am just saying it's actually not in the course. So expectation minimization clustering also will suffer from that minima. Agglomerative clustering gives you all possible methods of clustering a particular set of points, basically, right? It gives you, I mean, it just gives you the dendrogram and then you do what you want to do with the dendrogram. It doesn't matter. So it is not a what should I say? It is not an optimization problem sort of a thing. It's an algorithm, and after giving the algorithm, after the algorithm runs, it will give you the dendrogram. So there is no point of, if you are not solving an optimization problem, there is no point of convergence at local optima, and therefore k-means clustering and expectation minimization, both of them can get stuck at local minima. So yeah, and divisive clustering, you know, I don't even know what that is. So so agglomerative clustering, I think it's some variant of agglomerative clustering only.
Yeah,
so
divisive clustering is a
top down approach. Yeah. So yeah, so that is one. Yeah, so yeah, okay, so those are the three questions that I had for this thing. So any more questions, you can go ahead.
Sir, in agglomerative clustering, basically we are examining all possible combinations
Yes.
from the bottom up.
Yes,
correct?
yes.
So ultimately when we complete from bottom to the top, we know all possible combinations of clusters, then the choice is ours.
Yes, precisely.
Okay.
Yes.
Whereas in k-means, our initial choice dictates everything.
Your initial choice will dictate everything, correct.
Okay. In agglomerative, the choice is
Initial choice as well as the value of k.
Yeah. So, but agglomerative is more expensive, right? More.
Agglomerative, yeah, you will have to compute everything. K-means will converge very fast. Agglomerative clustering, yeah, people use it, but see, in most cases, for all practical purposes, k-means clustering will work just fine. Okay, agglomerative clustering is also used, but as you said, it's more expensive. It gives you the dendrogram, that's good.
No, but the problem is, see, basically agglomerative is nothing but set k is equal to 1, k is equal to 2, k is equal to 3.
Exactly,
And
exactly.
then 2 k-means. Basically,
Right.
each is a k-means only. K is equal to 1, 2 k-means. K is equal to 2, 2 k-means once again. K is equal to 3, k-means like that.
More or less, yes. I mean, what I am trying to say basically is, dendrogram is a very clean way of looking at the results of all of them together. Okay, and then select which one is my best clustering. So because it becomes a very graphical way of looking at the thing, therefore your clustering also becomes simpler. I mean, the clustering algorithm also becomes simpler.
Okay, sir.
Okay.
Sir, just a general
Yeah.
question, sir,
Yeah.
not related to k-means. Like we hear about normalization and standardization, right, sir?
Right.
So, what is the difference between these both? Like normalization or standardization?
Normalization and standardization, okay. See, I guess there are, I mean, the difference lies in the fact that normalization you can do it in multiple ways, right, and standardization there is a very fixed way of doing it. So standardization means you will subtract the mean and divide by the standard deviation, and normalization you can do, I mean, standardization is a way of normalization, that is one. You can also take the maximum value, divide everything by that maximum value. So that also is one form of normalization. Okay, so might be that is the difference.
So like in both normalization and standardization, always the
So if you
values will be between 0 and 1.
standardization of course might not be, because if you are subtracting by the mean, then it can lie between -1 and 1. I mean, it can even go beyond that, but mostly it will lie between some -1 to 1. So yeah, so because you are subtracting the mean and dividing by the standard deviation, some values can even go negative.
Yeah, sorry, means I meant -1 to 1. So in
Yeah.
both cases it will be between -1
If
to
you,
1.
for example, if you divide by the max of the maximum of the value, and if there were no negative values beforehand, if you just divide by the maximum of the of some particular value, then it will not introduce any extra negative values, but all your values will now lie between 0 and 1.
Okay. So means like which is standardization and which is normalization?
Standardization, if I understand, if I remember correctly, is the one where you subtract the mean and divide by the standard deviation, and normalization is a bigger term. I mean, you can normalize in various ways. So I have to check this also. I mean, I might mix up the two terms. I mean, is it very necessary that you know the two terms separately? Then I will check.
Because sometimes when we read, we see sometimes this term or sometimes the other term. So I was little confused, sir.
Sir, you see, some is English word, some is our mathematical word. But in the context of normal distribution, what you are saying is called normalization. You feel that subtracting from the mean, dividing by standard deviation. Is it standardization? I don't know. Maybe both are same.
Maybe finally both are same. Maybe, yeah.
Maybe one is English word, other is mathematics word.
Both of them are used quite interchangeably in machine learning. So, and both of them help equally, I guess. So that is why. So yeah. So that is why maybe both of. Okay, let me try to see what the actual terms are. I don't know whether I will be able to find it out, but let me try.
Generally, when we are not referring to probability distributions, a set of numbers are given. Say normalize it.
Yeah.
Normalize it means our intuitive understanding it, bring it to a common scale between 0 to 1 kind of. Okay. How you bring it to 0 to 1? What you said, divide by the maximum. That's what.
Yeah. So what I said was correct. So standardization is actually when you divide it, when you subtract the mean and divide by the standard deviation. So if because it becomes a standard normal distribution, more or less, that is why it is known as a standard distribution, standardization of data. And normalization is any way in which you can bring the length of your data to 1. Okay. So so for example, if you have a vector, so let me write here only. So if you have
very common in feature engineering. So
right.
One particular variable is varies from 0 to 1000. One variable varies from 0 to 10. Then we say normalize.
Yeah. So if you normalize that, that means you can divide it by the maximum of that particular value. That will bring it everything between 0 and 1. That is one way. The other way is if you take a vector, this vector, for example, you take the length of this vector. Okay, length of this vector means, I hope you know. So it's 1 square plus 2 square plus 3 square plus dot dot, that root over, and you divide it by every number by that particular value. Okay. So that so the length becomes a vector of length 1. So that is known as normalization.
Yes, that is the unit. Yeah.
So yeah, so that is the actual definition of normalization, whatever I mentioned here. But that division by maximum also. Okay, let's not talk about division by maximum. You have to do that in some cases probably, but that is not normalization in the true sense. Normalization is always dividing by the root over of the length of a vector to get it to unit length.
Okay, in case of normalization, so at the end it ends up between that -1 to +1 or so. But in standardization, since it is divided by standard deviation, it can be like in terms of multiples of standard deviation, like 1 or 2 or 3. It can be more than 1.
It can be more than one. Yes, it can be more than one also. Yeah.
Okay.
Yeah.
So in that case, might be in feature scaling, mostly they prefer normalization rather than
It depends again it depends. See, one thing which I can tell you is from my experience, if you don't do normalization or standardization, then your results will be very poor. If you do any of them, either of them, your results will be more or less similar. I mean, it's not that normalization will help you more than standardization or the other way around. More or less they will be similar.
And for k-means,
Yeah.
they always prefer to first scale the features and then do the k-means clustering, right, sir?
Right, because otherwise if you compute the distance between features, if your two features are of a different scale, other feature is completely of a different scale, then one feature won't play any part in your distance computation, the other feature will dominate. So that is why all of them are brought to the same scale.
How about for hierarchical clustering? I think the same thing.
Same
will be
thing,
followed,
same
right?
thing, same
Okay.
thing, yes.
Sir, for a decision tree, it doesn't matter, right?
Decision tree,
It doesn't matter because individually we are comparing the values.
Decision tree probably it won't matter, yes, yes.
Because we are not computing any distance.
Any
Individually we are
distance,
looking at it
yes,
computed.
correct, yes.
Okay. Other question, sir. Like
Yeah.
we're seeing leave one out cross validation.
Huh.
So like compared to k-fold cross validation, does it have low variance or high variance, sir?
Leave one out cross validation. High variance with respect to what?
Means compared to k-fold cross
No,
validation.
I mean variance in what? I mean, what are you computing?
So means if we try to learn the model using leave one out cross validation and learn the same data using k-fold cross validation. So what will be which one has more variance or less variance? Variance means it is with respect to test data only, right, sir? So it is more
Right.
overfitting to the train, and then it will not generalize well on the test.
So what do you think? So suppose validation you are doing for selecting your model, right?
Yes. So might be in k-fold we are validating, we are kind of splitting it into k subsets, and
Right.
then we are validating with respect to k items.
Right.
No.
Right.
Whatever the items in that one subset.
Yes,
So,
yes.
But in leave one out, we are like taking except one, if the sample size is n minus 1 we are taking to train, and that only one sample we are taking to test.
Right.
So
yes.
I thought might be in that case variance would be more, right? Because sometimes we train. I was confused, sir. I wasn't able to.
Sir, my answer, I have a general confusion. The variance, can you just illustrate the concept of variance? Is it variance on y value or x value? Just take an example of linear regression and try to illustrate the variance.
Y value, always y value. Variance is with respect to the result that you get.
So that means for the same independent variable x, if there are multiple y's, okay, that is variance is high.
For the same independent x, if you have multiple values
x, there are multiple y's. No, I want to get the intuitive feeling of the variance concept.
Variance means whenever your x changes slightly, if you see a wide change in y, that means your model has a high variance.
No, naturally when x changes, y also changes.
No, if you see that if your x changes by 0.1, right, and if your y changes at the if your x, so suppose you have two models, both modeling the same function, trying to model the same function. In one case, if your x changes by 0.1, your y value changes by 10. In the other case, if your x changes by 0.1, your y value changes by 1 lakh. The other model higher variance, yes.
Okay, so we prefer low variance.
Of course, yes. And the other question that was asked, I mean, I thought your thought process was correct. I mean, the way you were thinking, it was correct.
Okay, in that case, if it is only leave one out, then in that will be high variance.
Probably,
right,
yes, yes.
Okay. but means sometimes when I think a little bit differently, I feel like in leave one out, you will get more data to kind of train the model. Only one will be left out, as if
Right.
it's like a test item.
Right.
So in that case, your model should be like less overfitted, right? Then variance should be less.
So you are saying
sometimes
that,
feel that.
yeah, you are saying that you are giving more amount of training data, right, and you are selecting your model based on the performance of only one data point.
Right.
So that means that your model has a chance of overfitting to your training data more, right? You have more training data to look at, and maybe because of, I mean, the k-fold, I mean the single data example that you got was very similar to, somehow randomly it became very similar to one of the train examples. So your model will start overfitting.
Okay.
So it will have a higher variance.
So in case if in k-fold you will have more number of samples to validate on, then the
Right.
probability of overfitting will be
Yes.
Sir, one general question. Okay, the same model. Suppose if the training data is increased by twice.
Right.
So overfitting is chance is high, right? When the training data is more.
See, these are very subjective questions. Okay, I mean these are like, there are no correct answers to this. So I can tell you this, that if your model is okay, so if your model is powerful enough that it can learn from those double the number of training points, then your model will learn. Okay, it depends on this, it depends on the capacity of your model also. It's not like the more amount of training data you give, a model will continue learning that. It's not like that. Your model also needs to have the capacity of learning from those extra data points.
Okay. So intuitively I am thinking is, let us say we have only one data point. So very general. So so if you give more and more points, it is closely resembling the underlying model. So it is closely overfitting the data. As you get,
suppose you give only one data point. Suppose you are solving linear regression and you give one data point.
Right.
What do you think your training error would be?
Training error.
It will be 0. Whatever you do, it will always go to 0. Okay, so it will always go to 0. Now if you add, so that is why you cannot say that if I have very low data points then my model won't overfit. I mean, if you have very few data points, then your model also will start overfitting. It will learn only those points, and it will be, your training error will be 0. See the, okay, so see.
No. So suppose let us say the training data contains only 1 point. The training error will be 0, but the test error can be
huge. It will be huge, right? See, the thing is, the main point of machine learning is this, the data. Now what is the data? Suppose in the entire universe, this is your data distribution. All data points that are there in the universe comes from this particular distribution. Okay, some data distribution is there, somebody is maintaining this data distribution,
which we don't know,
which nobody knows.
Yes.
Okay, this runs into trillions and zillions maybe. Now when you are actually learning a machine learning model, you are given a snapshot of this distribution. So your data distribution is probably just this much, which is just a snapshot from this big distribution.
Right.
Now what overfitting and underfitting means is, first of all, what is underfitting? You don't even try to model this particular data distribution. You don't even know what this data distribution looks like. That is underfitting, right? What is overfitting? Now when your training distribution comes from here, maybe your test distribution comes from here, very close by, but it is not exactly same.
Right.
It's very close to your train distribution, but it's not exactly same. It's not from the same it's not from the same part of this entire data distribution, let's say. Then what you do is, if you learn this distribution too well, then you can't generalize also to here. So entire goal of machine learning is to look at the training data and be able to understand, okay, so if I am given some training some test distribution which is sufficiently close to my training distribution, can I generalize to that? Now suppose if you are given only 1 point from this distribution, you can't hope to generalize to a distribution from 1 point, or even from a very few, from 10 points or 100 points also. You need to have a large number of points so that you should be able to at least learn something about this data distribution. Only then.
Okay. I got it, sir. So the moral of the story is that, see, the underlying hidden distribution is something we don't know. Only
Yes.
God knows.
Yes.
But given the training data, it is expected that we must have some error. Okay.
Yes.
To take care of the hidden thing.
Right.
We
Yes.
should never overfit. We should never fit a model which is perfectly, training error is close to zero.
No.
We should never do that.
No. And the other thing is, if your model is very strong, then whatever training data you will give, with time the training error will come down to zero.
Yes.
It will be able to fit. Neural networks are that strong that they will finally be able to fit to any training distribution if you have set all the things correctly. Of course, if you are using a one layer neural network and hoping that it will fit, of course it can't do that. If you have a proper neural network which is sufficiently powerful enough, it will be able to fit your training data quite well.
Okay, that means it is close to overfitting only. Okay.
Yes, it will try to overfit, and that is why all those regularization things are useful.
Okay, sir.
Hello, sir.
Yeah.
Sir, one other question from the previous year, sir. So it is like they have given a truth table like A and B and function of A and B.
Right.
And they are asking if can you represent the following Boolean function with a single logistic threshold unit, that is a single unit from a neural network.
Okay.
So I can say like A and B is 1 1 means 0, 0 0 means 0, 1 0 means 1, and 0 1 means 0.
1 1
So
means 0.
0 0 also is 0.
Okay.
Okay, so but 1 0 is 1.
Right, this one.
1 0 is 1, and 0 1 is 0.
0 1 is also 0.
Yeah, if it was this, then I thought it was XOR, but here it was this. So I wasn't able to find out what type of logical
So
basically these 3 points are the zeros, and this is 1.
Network with one layer, I was told, can learn any Boolean function, so it should be able to learn.
No.
Just a
It
minute.
needs 2 layers for XOR function. One layer is only for AND and OR. Minimum 2 layers, it can learn any Boolean function. Confusion always about that number of layers.
See, output we should not include. Sir, in neural network, how to count
Yeah.
the layers?
Yeah, sorry,
one
I
layer,
got
does it
disconnected.
mean-
Just a minute, yeah. Yeah, I am audible, right?
Sir, the confusion is in a neural network, counting the layers. So, when we say one layer network, does
Right.
it mean that
Always number of layers means number of hidden layers.
hidden layers?
Yeah.
So you should not look at input and output.
No.
So, two layer means the two hidden layers.
Yes,
That means input layer, two hidden layers, and output.
output layer, yes.
XR function, to realize XR function, we require only one hidden layer.
XOR function, no, I am thinking about this function.
Yeah.
What was the question again? Can you please say?
Somewhere I have read, sir.
Hello, am I audible?
Yes, you are audible, sir.
Yeah, can you please reiterate your question?
Yeah, I can read that question, sir.
Yeah.
Can you represent the following Boolean function
Yes.
with the single logistic threshold unit? That
Sing-
is a single unit from a neural network, and the truth table is given, and answer options are yes or no. And the answer is given is yes, but I don't know how they are trying to get that.
1 1 0 0 0. So you by neural network you mean I can have as many neurons as possible, is it?
No, that is a single unit from a neural network is what they're saying.
A single unit.
Yeah, a single unit.
Single threshold logic. Output. When I say threshold means is output, right?
Yeah. Okay, so one thing which you can do here is, okay, so let's say I have 1 plus 1, okay, and so the challenge is between 1 0 and 1 1, right? That will be the challenge.
Yes,
okay. So if I take, yeah, so if you do something like, I'm not sure whether this is,
so is it might be something like for logistic, because there the question is with a single logistic threshold unit, and in the bracket they are saying that is a single unit from a neural network. So logistic threshold unit means they can do a logistic regression.
see, first of all the thing is you need to plot this, right? So you can see my plot here, right? This is 1 1, this is 0 0, this is 1 0, right?
That is 0 1, right, sir?
Sorry, 0 1, and this is 1 0. So you can always learn this classifier.
Right. Okay. So that is why you can learn it from the single.
So that is why you can just say yes, because if anything can be separated out by a linear classifier, the logistic regression would be able to learn it. Now what it will learn depends on the logistic regression only. I think it will learn some it will learn a thing like some x bar plus y or something. It will learn something of that sort. It will learn. Okay, so if you see that,
one layer only, sir. One layer only. Right?
This is not, she is not saying about layers of neural network. It is, she is just saying a single logistic regression model.
No, that is output. Output is.
No, she is saying a single logistic regression model. She is not saying anything about the neural network.
What do we mean by single?
So logistic regression. So if you
Logistic, okay, sir. My mind is still in neural network.
Sir, there is a point in the bracket they mentioned about neural network. That is why it was confusing, sir. So what they say is, with a single logistic threshold unit, in the bracket they say that is a single unit from a neural network.
So that means, okay. So I think I had referred to this when I was talking about neural networks. So this is a neural network, right? Finally, I am doing a binary classification, but this is a neural network.
Right.
Yeah, when we
Correct.
think of finally, there must be only one only.
So this is nothing but a logistic regression.
That is only one unit.
And this is actually a logistic regression model. Okay. So you are getting some, so then what is the difference between logistic regression and neural networks? In logistic regression, the features that you are giving to the model, you have to learn it yourself. You have to provide it yourself. Here the neural network, by means of all these connections and nonlinearities, will learn some function so that it becomes very easy for a logistic regression model to classify it. Is my point clear?
Okay.
So
Yeah, it is kind of, in that case, neural network, we can see it as like feature extractor.
exactly,
All feature extractors cascaded,
Precisely.
and the last there is a classifier.
Precisely.
Or any kind of algorithm. So
Right.
it can
Yes.
be linear classifier, linear regression, or logistic regression,
Precisely.
or anything.
Precisely.
Okay.
Yes. And this problem you don't need to find out what the classifier is, just because it can be classified by linear classifier, logistic regression will be able to find it.
Okay, got it. Yeah, it was tricky because I was trying to see if it was not even AND or XOR.
No, I mean you can just draw and see these things.
Okay.
For example, I think there will be cases like, I mean when 0 1 and 1 0 will be 1 and the other two are 0, in that case you won't be able to classify by logistic regression. I think that is all right. If
Yes,
this is
it is
1,
XOR.
if these two are 1 and these two are 0, then you won't be able to have a linear classifier.
Okay. So that time, how many layers of
I think 2
neural network
layers
is
will
needed,
suffice. 2 layers will suffice.
So when you say 2 layers, it means one hidden and one output, because that is what was given in the
sir.
notes.
No,
One
two,
layer only. One layer is
one,
enough.
one layer, yeah, one hidden layer is enough. Yes, yes.
Because somewhere I read, sir, one statement that any Boolean function can be represented with one hidden layer.
Yes. So, but the caveat.
But in the notes, right, it is little bit contradicting. It says a 2-layer perceptron can represent an XOR Boolean function. So that is why a neural network with one hidden layer is called 2-layer neural network. Such neural network can represent all Boolean functions. That is what
Yeah, that's
given
where
in
confusing.
ma'am's notes.
How to count layers? No, that's where difference.
So that is why I thought, by reading her ma'am's notes, I thought might be layers is always, it includes output layer also. Hidden plus output is called layers, and in case if they mention one hidden layer, then it is one hidden plus one output. Otherwise, they mention the one hidden layer is also called as 2-layer neural network. That is.
Let me try to draw this. Then I will also become. It will also become clearer to me. Okay. So this is my input. These are my hidden layers. Right. Suppose I have a hidden layer. These are my inputs. This is hidden layer 1. This is hidden layer 2. This is output. Yeah, inputs. These are my inputs. These are my, okay, these are my 2 hidden layers. I think I'm mistaken. I was mistaken. These are known as the hidden layers. Output layer is never known as the hidden layer, but together with the output layer, the 2 hidden layers, this will be a 3-layer neural network.
Because sir, input is actually not a neural network.
Yeah, wherever you learn, wherever you have weights to learn, those many layers will be known as the, I mean those set of weights will constitute the total number of layers. Yes.
So for example, in this diagram, how many weights? W1, W2, W3, 3 layers are.
Yes. So this will be a 3-layer neural network. Yeah.
Okay. So in that case, for any Boolean function, we need a 2-layer neural network.
Yes.
For
all Boolean function. Basically, it can be said that for all functions can be represented by a 2-layer neural network. But the trick to that is somebody comes and needs to tell you the number of neurons that you need to put. Okay. So unless you know that, then you can't claim that your neural network can learn everything.
So the trade-off is whether you increase layers horizontally or you increase the depth vertically, the number of neurons. Okay. So for example, you want to model the same function. You can do it by increasing the layers, keeping the height of neurons same, or increasing the number of neurons, reducing the layers. Both ways it is possible.
Both ways it is possible. It depends upon your choice. It is up to you what you want to do.
Oh, in both ways we get type of a same result only. So
again, that depends upon your problem. That nobody can say for sure what you will get.
Okay, then we have to every time we have to play n number of iterations and see increase.
Generally what will happen is, I mean, at one point of time you will also get an understanding about what is happening. I mean, if you increase the number of neurons, in many cases it will happen that okay, nothing is happening, nothing extra is happening. Okay, then let me increase the number of layers by keeping the number of neurons same. Right, so that way it will continue, and one point of time, of course, see, the thing is, the neural network that you end up with may not be the best neural network. It won't be the best neural network, but you will have to live with it, because it's a heuristic thing. So you have got some results to back your claim that your neural network performs reasonably well. That's the only thing that you can claim. Other things you can't say.
Okay, so neural network cannot learn by itself how many number of neurons it
No,
can
no,
put in a layer. Okay.
no, that it can't do. At least till now it can't do. We don't know about the future.
Maybe for that another neural network is required to learn number of neurons.
Yeah, maybe.
Okay, sir, this is clear, sir. Sir, another one regarding hypothesis space, sir. So this is
Yeah.
one more question. So
Huh.
it was like, what is the purpose of restricting hypothesis space in machine learning?
Huh.
So can be easier to search, or another option is may avoid overfit since they are usually simpler. Example, linear or low order decision surface. Or the third option is both of them.
Right.
So,
Is the answer both of them?
yes, sir. The answer is both of them, but I couldn't understand that B option, sir. So can be easier if I can restrict hypothesis space. It is easier to search. It is that is obvious. But may avoid overfitting since they are usually simpler.
See,
in the bracket it says example linear or low order decision surface.
Right. So for example, okay. Suppose
I'll tell you my confusion, sir. So restricting hypothesis space, again, ma'am was explaining regarding bias. So in bias, she explained two types. One is restriction and one is preference bias. Restriction, she told, okay, we can restrict which type of hypothesis we can select. And preference, we can select either which polynomial degree or n degree we want. So here, the second option, for me, it felt like that n degree, like preference bias, not like the restricting hypothesis space.
Right. Okay. Got your point.
Sir, just to add to that, for example, in polynomial regression, simply speaking, the hypothesis space is infinite, right?
I'll tell you. I'll come to this point. Yeah. So suppose in polynomial regression, I have x2 x to the power 5. Correct.
Okay.
And suppose you. So these are, I mean, you will learn the coefficients for this, right? You will learn W, you will learn W1, W2 up to W5, correct? You will learn these 5 things. Got, is my point clear?
Along with W0 also, right, sir?
The bias you leave for now.
Okay,
Bias you leave for now,
it.
you have W1 to W5. So you have W1 to W5, you have x square up to x to the power 5. Now you let your model learn something. Your model gives you a line or gives you the hypothesis, if I may call that. Yeah, your model gives you the hypothesis something like 100x plus 1000x square plus 1000x cube plus no I am just putting some numbers for fun, plus 10,000 x5 x to the power 5. Okay, so these are your W values.
Okay, sir.
And you see that your model is overfitting, right? You see that your model is overfitting. What will you do? What is the solution to overfit? I mean,
regularization.
You will do regularization, right?
Yeah.
So what will you do? You will add something like this particular thing. You will start adding.
Right.
Now, whenever you add these sort of things, what will your optimization problem try to reduce? These.
Overfitting?
I am saying that in terms of these values 100,
Oh,
1000,
use those weights. Yeah.
it will start to reduce these weights, right?
Right.
So when you are reducing these weights, your model is becoming from a 5th degree polynomial to close to a 3 degree polynomial. This weight is very low. From 10,000 it has come down to, let's say, I mean, of course it won't be 10,000. If it is high, then it will come down to, let's say, 0.1, and this is also 0.9, let's say. Suppose I am just giving you an example. So suppose by regularization you have brought this down to 0.1 and brought this down to 0.9. Then can you say that your model is more or less a 3 degree polynomial or 4 degree polynomial, whatever, 3 degree polynomial?
Yes, sir.
So has your hypothesis space become simpler to learn?
Yes.
Yeah, so that is the
But that is this is regularization, right, sir? But
Huh.
the question was, what is the purpose of restricting hypothesis space in machine learning? And that option was may avoid overfit since they are usually simpler.
so how did you come to this why did you do regularization? Why did you
Again,
stop overfitting? So when you see that when you are trying to stop overfitting, your hypothesis space is actually becoming simpler. Is my point clear? You were not trying to do anything with the hypothesis space, let's say. You are very happy with the fifth degree polynomial that you are having, and now you are just seeing that, okay, it is overfitting, okay, let me add regularization. You are seeing by means of the regularization your hypothesis is actually becoming simpler. So that means overfitting is directly related to your hypothesis becoming simpler.
okay, which is nothing but it is kind of reducing my hypothesis.
Exactly. So
Okay.
so that is okay, so let
Now
me
it was from x5, from the x5 5 polynomial, now it has reduced to x3. It
more
means
or
it
less,
has
approximately.
reduced my hypothesis.
Yeah. See
Sir,
the other thing, let me complete. See the other thing is, I mean, this question that was asked actually can be answered in a much better way. Okay. You remember there was something known as MLE estimate and the MAP estimate, maximum likelihood estimate and the maximum a posteriori estimate.
Yes, in this Bayesian
Right.
way, right?
So so MLE estimate is actually, I mean, I will not explain this because this is, I don't know whether this was taught in the course, but basically what you need to do is, if you do MLE estimate, that means your hypothesis space is unbounded. Anything on the face of the earth can be your hypothesis, right? MAP is actually better. Why? Because you know that you have some prior knowledge of how your weights should look like. So I will just state this here. So this is the normal distribution. This is the normal distribution. So if you say that my weights, all my weights are coming from a standard normal distribution, if this is the prior that you are trying to enforce upon your problem, that all my weights are coming from a standard normal distribution, that is precisely equivalent to putting this lambda by 2 norm of W square in your problems. I mean, I will not explain this, but just know that this is a fact, that if you say that my W should be so what does this mean if I say that my W lies between, comes from a distribution of normal distribution, standard normal distribution, that means more or less it will lie between -1 and 1. That means my W cannot grow very high. If the total norm of W cannot grow very high, it cannot have very high degree polynomials also. That means I am restricting my hypothesis space by means of this regularization, and regularization in turn reduces overfitting, and therefore by restricting the hypothesis space I am trying to reduce overfitting.
Okay, understood, sir.
Yes, sir. So coming to the definition of hypothesis space,
Yeah.
You said is infinite. For example, let us say a 3 degree polynomial. You written x, W1x plus W2x square plus W3x cube.
Yeah.
So theoretically, the hypothesis space for me it looks like infinite because W1, W2, W3 can be minus infinity to plus infinity.
You are saying that, I mean, now we are entering into a dangerous conversation, saying that now which one is a bigger infinity now, because you have left out W5 to W infinity also.
Yeah, each of the weights.
Each of the weights can be fine. Whatever you have said,
dictate one hypothesis.
each of the weights can be fine. I mean, I am not arguing with that. What I am saying is, you are saying that 3-degree polynomials, all my weights can go from 0 to infinity. That means minus infinity to plus infinity. That becomes my hypothesis space.
Yes.
That is fine. What about all the 4-degree polynomials where all the w's from minus infinity to plus infinity, I mean all the weights can also range from minus infinity to plus infinity, which no, which infinity is smaller?
Yeah, the first one is smaller.
Exactly. So that means you are restricting your hypothesis space.
Yeah, so actually these problems come only in the continuous regression. In classification, actually we can have a finite hypothesis, correct? Classifications.
What do you mean by finite hypothesis? I am not sure.
So in classification problems,
Yeah.
in classification problems,
No,
let us say,
classification is just regression with a sigmoid at the end.
no, for example, all the feature variables are binary.
Right.
Assume classification, let us say we have 10 feature variables in classification.
Why will you have all the feature variables binary in classification?
Okay, hypothetical case, let us
Huh.
say, now the hypothesis space is 2 to the power of 2 to the power of n. That's what Madam told.
Yes.
That is finite whole number.
That is finite. That is finite. That doesn't, I mean, of course, I mean, if your features are that way, then it's very good. I mean,
Only the problem comes in a continuous.
yes. I mean, don't think about this infinity and all these things. I mean, it's better to just think of, if my 3-degree polynomial, I mean, when I am talking about restricting of hypothesis space, that means I am not talking about restricting the weights of, I am not talking about 100-degree, I am talking about not going about, not modeling my, not using a 100-degree polynomial for modeling my particular problem at hand. I am talking about a 2-degree polynomial, 3-degree polynomial. That's it, nothing more, nothing less.
Okay,
Sir, about our like, is this the last session, sir? Or
Yeah. This will be the last session. Yeah.
Means, is it like possible, sir? Like, because we couldn't get, might be if we revise, we might get some like doubts like this. Is it possible, like Friday, like how you conducted, right, sir? This Friday, at least, if you can.
Let me see that. I'll talk to the NPTEL people also, but let me talk with them and see.
Okay, sir.
Yeah.
That would really help, sir.
Okay, sure.
Sir,
Yeah.
see, for example, in support vectors, and there are so many equations are there.
Yeah.
Okay, do you have to remember that to answer the exam, all that equations?
This I am not sure, because I will not set the questions.
We understand the concept, support vector.
Yeah, basically I will not set up the questions. I am not even closely related to setting the questions. Okay, so
Because the slides are all full of.
yeah, I know support vectors can be tricky, but I think it will, I mean, you can ask the TAs of this course. It should mimic your assignments only. That's what I feel.
Sir, how many questions would be there in the exam?
No idea. I don't, you can ask the TAs about this. I mean, you can ask in the forum. I am not involved in the question setting or anything of that sort.
Okay, sir.
Okay, if there are no more questions, I'll close the session. Thank you. I'll see whether we can meet again on this Friday. Thank you.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you, sir.